Summary, what I'm going to talk about today is first, I will introduce two different modeling approach, a widget approach and manual approach. Also, I will be focused on steel composite widget capability in terms of modeling bracing systems. Secondly, I will discuss what is the main feature in widget modeling and how to use the steel composite widget. Next, by using node and element approach, you can easily make different types of bracing system without any limitation. So, a little bit about the procedure of modeling in node and element approach will be discussed. Finally, I'm gonna explain how to do design check settings. Especially here, I will prove the logical sequence in design check setting to give you a better understanding. The first topic is a comparison with a widget approach to manual approach. Before you use Midas Civil for steel top design check or load rating, it will be helpful for you to understand the exact capability in two different approaches. First, both widget and node and element are fully available in any horizontal alignment type, such as straight, curved, skewed, and even vertical alignment. Also, the capability in designing bearing, pier cap, column, and top box section modeling are the same. However, widget can automatically generate those features with ease. However, the availability of making bracing shape in the two approaches is different. You can make a single beam between two or more top box sections through the widget. Node and element approach has more broadened capability than widget. In node and element approach, you can create any bracing shape you want. However, even in widget, if single beams have enough stiffness and the number of cross frames are geared in a bridge, there is no problem with designing steel top and box girder lines. Today, I would like to address bracing system modeling since I know most of our clients know how to create steel composite top bridge by using the steel composite widget. And the process is very easy to understand. So I will be focused on the how to model the bracing system. Here, I would like to suggest the most efficient way for you to model a steel top bridge for design check. The widget approach shortens a big amount of time in setting up a horizontal alignment and vertical alignment. However, creating our bracing systems details are weaker than the node and element approach, I mean the manual approach. So first, by using the widget, you can build up the basic frame in horizontal alignment and vertical alignment and defining the other load such as wet concrete loads or wearing surface loads. Also, the construction stages are determined with ease through the widget. Let's assume you model the invented K bracing system like a picture on the right hand side. First over, from the given top diaphragm location information, you can define the node location for the top diaphragm in the widget. Again, the widget only can do the single beam cross frame. Once you create a rough bridge model, you can delete all the cross frame, leaving the nodes which are created um, where the single beams are located at the right end and left end through the widget. From there, you can start modification to create more complex bracing system and then do design check setting. Okay, now let's move on to demonstration for using steel composite widget. Give me a second. So this is a steel top bridge model I already made before I came here. So I will just compare the model and I will explain how these numbers can be applied to this like a bridge model. So some of you guys might be familiar with steel composite girder bridge wizard, but there would be some like a new like a users. So I will just briefly go over the how to use a steel composite girder bridge wizard. So you can save your wizard file and open a wizard file whenever you want. So right now I will just open up the wizard file I made it before. So this one is the same as the steel eye girder composite bridge wizard. So on here, girder type, you can select the composite steel box or composite steel top sections. And modeling type, you can select the two options, R frame, deck as plate, girder as frame. So this span information, as you can see here, this is a 3 continuous beam. So you can punch the 120 comma space 180 comma space 120, and then you can select the you can punch the deck width, and here layout offset. This one represent like a reference line. So if you just set the layout offset as 0, which means the reference line go through the center of the deck. So for the boundary condition, before going to boundary condition, you can also make the curved bridge by putting the radius number. So boundary, you can just model a bridge with a substructure or without substructure. So here I just made as you can see here, this is a pier cap and a pier columns. So I made a substructure on here. So check on the pier cap box, and I already made some sections before I come here. So those are the pier cap sections, and also on here you can define the length of the pier cap, and on here you can define the material property on the right hand side, and a column you can define the height, and once you click the guide on here, give me a second. You can see more detailed information on here. So for the sections, basically you can define the structure deck thickness on here. I just made it 0.5 feet, and the number of girders is this one is for the girder offset with transverse directions. So as you remember, I made a layout offset as 0. So this one is two steel top sections. Is apart like a 12 feet apart with transverse directions at the from the reference line. And the transverse deck element is for the dummy deck. And in the bracing information, as you can see here, once you click the bracing details, you can select the single beam on here, and also you can select the element type, like you can make it truss or beam element. Also, you can select where you're gonna put the single beams. With regards to like a top flange lines. So I just made it 0.5. So distance from the top flange to the single beam center line of the single beam will be 0.5. And you can modify those properties, and you can add those property or just modify. Click this one and click modify. Also, you can make the spacing with the 3 options. Just if you make it 10 division, select the division options, or you can make it distance. You can just punch the like distance, or division per span might be each span you can make the divisions. So let's say we have 3 spans, and the first span, if you want to make it like a 5 division, you can just type the 5 and comma, and a second span, if you want to make a 10, you can just punch the 10. And this is a straight bridge. You don't need to modify those stuff. And this girder information is for the longitudinal directions. Along with the longitudinal direction, you can change the section property. So as you can see here, along with the longitudinal directions, you can see the different sections located at different locations. So here you can make a number of division on here, and you can also copy, if the first girder line is the same as the second girder line, you can click these buttons, copy to current girder data to other girders, and then move to this selected list and click OK. You can see the same girder section property is copied to the second girder line. So these are the loader informations. Let's say B1 and B3 and B5. So B3 represent the median strip locations, and then B1 and B5 represent the barrier load locations. So those are, you can define on here, but make sure the total of the sum of the B1 to B5 should be exactly the same as the deck width on here, on the layout tab. And the good thing about Steel Composite Bridge widget is load can be defined automatically inside of the bridge widget. And once you create a bridge and all the information is included in from this widget, is very easily can be easily defined. So once you create your bridge through the widget and go to tree menu, and you can check all the load and construction stages are stored from your punching numbers. So here wet concrete and formwork, barrier, median strip, and this one could be divided for the two different situations, before composite and after composites. So you can also punch all the numbers you need on here for the load. And in here, Steel Composite widget bridge, Steel Composite girder bridge widget, you can define the moving load cases, H to LLFD, and also you can select the traffic lanes and define the vehicles on here. So in construction stage, you can freely modify the deck sequencing. So once you click that split construction on here, you can change your sequencing of the deck construction on here. So after you create your steel top girder, steel top bridge through the widget, you can see this model, as you can see here. So as I mentioned before, making steel composite top bridge is very easy when you are using steel girder bridge widget. But if you start this modeling from the scratch by using node and element approach, that will be take much of time for you. So that's why I recommend you to first, for the rough design, like a primary model, you can just create this model through the widget. And if you want to put some more like a complex bracing system, let's say inverted K brace or top flange lateral bracing, you can do some modification inside of the section in steel top sections. So, but as I mentioned before, those are the single beams. I want to leave those nodes around like a steel top, because these nodes can be used for defining top diaphragm in inverted K bracing. So let me show you how to do this one. So first of all, go to tree menu and only activate the cross frame. And use the select all. As you can see, red highlighted line is on the each beams. And as you can see here, node information and nodes are selected and elements are selected. So on here, you can just delete all the node information on here. Excuse me, just get rid of the all the elements selected. And hit the delete. Give me a second. There was some mistake on here. So let me show you how to delete the element, the single beams, leaving the nodes information on the dead locations. So again, I'll go to tree menu and double click the cross beam on here. These are the like a single beams are selected. And activate only cross beam on here and select all, and you can see nodes and elements are selected. So I want to leave the nodes information on here, so just delete the node information on here, which means if once I hit the like a delete key, the element will be deleted, but the nodes nodes remains at the same locations. As you can see here, these nodes around center to center inside of the steel top sections will be used for the top frame for modeling the inverted K bracing system. So let me move on to let me briefly go over the different type of bracing system with a different purpose. So first, internal and external cross frame bracing can be observed in most of steel top bridge. I might guess that the most general case will be the inverted K bracing system as shown here. The reason to put this kind of bracing is preventing or controlling cross-sectional distortion when the wet concrete pours onto steel top sections. Secondly, top flange lateral bracing is used for resisting shear flow from the non-composite loading. Today, I will show you how to create a inverted K-bracing system modeling and Warren type lateral bracing system. So how can you model the inverted K bracing system and Warren type lateral bracing system? So for that, node location study should be conducted to accommodate all the bracing shape. So the first solution would be that like multiple nodes are required to make all the possible bracing shape feasible in Greeley's model. So as you know, in MIDA Civil, in Greeley's model, like a beam element, steel top sections are expressed by one node, but there would be 4 or 5 connection dots required to connect the K bracing system to steel top sections. So the first, we need to know how to create a node and a translate node to find and place the proper node uh, on the top section lines. And multiple node information should be identified as one of the top section nodes. So if you just put the nodes, and even if you connect the K bracing system onto steel top sections, if you don't connect them to the nodes representing the steel top sections, the nodes has the nodes, the other nodes don't have any meanings. So you need to connect them through the elastic ridge link. So I will cover how to connect the nodes through the elastic ridge link. And yeah, also the translating node skill is a key feature to shorten the modeling time. So for the putting the nodes on the different location on the steel top section lines, you need to know the coordinate for each node. But if once you create the nodes on the one side, let's say just left side, and you know the distance on y-axis, you can just translate node on the other side. So that will be easy for you to create different nodes on the steel top sections. Let me show you how to do that by using pictures. So I will just model this inverted K bracing system. So as you can see here, I create a different node. Before that, this red dot represent the steel top sections. So from here, I just made a 1, 2, 3, 4, 5. Those 5 nodes, and I just translate to the other side. So and you can see here these nodes already I made in steel composite through the steel composite bridge widget. So on here you can just create a node and then translate a node using the a copy and type the dy and just create a nodes on the other side. Before then, those 2 nodes on the top flange is for the lateral bracing, and those 1, 2, 3, 4, 5, 6 nodes, 7 nodes for the this K bracing system. But those nodes are floating right now, so we need to connect them through the elastic ridge link. So this red dot represents the steel top sections. So between those nodes should be connected by elastic ridge link. And finally, these nodes also connected to this red dot by using elastic ridge link. From here, you can, once you set up all the elastic ridge link around the steel top section lines, and you can create the element on here. Under node and element tab, and you can click the create element button, and you can define the section and material property for the cross frame, and you can connect those dots to mimic the inverted K brace. Also, on here, don't never forget the check on the two box, copy node attribute and copy element attribute. If you don't check on those two box, you might lose elastic rigid link property, because those nodes also contain the information about the elastic rigid link. So you should check on those two box. And once you complete these one sections, and you can copy the node and element for the inverted K bracing system, and copy to the other the other sections, segmented sections. So let's say you can select those nodes and inverted K bracing system elements, and copy and paste to the along with the horizontal alignment, and you will see that all the bracing system will be copied to the other sections of the steel top. And this one is for the variant type lateral bracing. So as I mentioned before, two nodes are located on the steel top steel top flange. So once you first go to top view, and you will see these views, and just connect those dots to complete the variant type lateral bracing. So let me just summary what I have done here. So the initial model from the widget contains nodes around the center to center location on here. And also there is a construction stage information, and before composite and after composite, and also static load. So you don't really need to create a construction stages or define the load if you use the steel composite widget. So first, you need to use a steel composite widget to create a love model file. And then, as I covered before, as you can see, just using the node and element, you can create an inverted K bracing system, and copy all the information to the other steel top sections on the horizontal alignment, and then you can connect the element through the to make the lateral bracing system. So that will be R. And let's move on to how to do design check setting. So what we have done is for the process for just create a bridge and define something. But let me just go over what we have done before until now. So we create a steel top sections and cross frames and longitudinal stiffness. This one will be covered later on. So those material and section properties are defined in one steel top section bridge. And then, because you use a steel composite widget, support are automatically defined and also you made a pier cap and a pier columns. So there is a link is automatically generated between the substructure and the superstructures. Next, static load and construction stage load, and outside of the widget, you can also define the moving load on more details. And once you after you complete those steps, and go to widget tab and click the load combination buttons, you can do auto generation. So those part is I guess those parts are very procedure for the find the ultimate resistance. But from now on, we're gonna cover nominal how to find a nominal resistance. So after you complete your model file, and then for going to design check, you need to define the resistance factor on the right hand side. And also, if you have a different material property on top flange, web flange, and bottom flange, you need to set up the hybrid factor. And also, if you have a transverse stiffener, you can also define in design check settings. So we make the composite sections because we define the concrete, deck, material property, and steel section and material property. So in section property dialog box, but we didn't define the shear connectors. So we're gonna do this. We're gonna define those stuff, and also we didn't define the umbrace length for the lateral torsional buckling. Next one is a design position and a position for Excel report. This one will be covered later on. So this is a resistance factor. First, you need to define the code like H to LRFD 12, and you can modify the shear strength resistance factors on here. And if you are using the multiple box sections, you can just consider the distortion and distortion stresses, and never forget to check on those design parameter box, because if you don't check on those box, those like design check tables will be grayed out. And this one is for hybrid factor. If you have if you are using a different section and material, the material property on like top flange and web flange and bottom flange, you can just click this, check on this box, and you can define the different material property on here. Also, you can renew your concrete dam material sections. And before you are defining longitudinal reinforcement, you can also define the steel strength material property on here. And from now on, I'm going to talk about the longitudinal stiffener. So longitudinal stiffener can be defined in section property dialog box. So here, once you click the stiffener button, and you can see on here, there is 3 different types, a T and a flat, and I guess it's a U rip. And on here, I just made a T, sections. And once you create those things and put it on this box, and here's the thing: if once you click this box on C columns, and if you don't check on this box, there is no effect on structural analysis before design check. But if you check on this box, this longitudinal stiffener effect, this like longitudinal stiffener, like something like section property, and in terms of strength, or like a moment or shear, can influence on your structural analysis. Like when you're creating moment or shear diagrams, you can see the slightly different between unchecked C columns and checked C columns. Those are the shear connectors. Yeah, I just bring the pictures on here. As you can see here, pitch is distance between the 2 shear connectors with longitudinal directions, and height is for the shear stud height, and spacing shear connector will be a transverse distance between the 2 shear studs. And a number of shear connectors, once you find it, and you can just punch the number on this box, and the length between max moment and zero moment. So before you do the design check settings, you can check your moment diagram. So you can just create your moment diagram by performing the structural analysis, and you can check the distance between the max moment and zero moment and punch the number, and a shear connectors setting is done. Give me a sec. And now let's move on to how you can do the like a design check settings. So under design tab, first you can just select the edge to LRFD12, and as you can see here, you can define all those things. Those are very easy to be defined, but let me pick up some points on here. So I explained the design material on here, and I click this composite material, and as I mentioned before, if you have a hybrid factor, and check on this box and modify the different material property on different locations on here, and also reinforcement selection on here you can define on here. And this is a load combination type because I use the auto generation like a load combination, and those like a strength limit state and service limit state and fatigue limit state is already categorized on here once you make your load combination through the auto generation. And a transverse stiffener and umbrace length on here I already defined on here. You can select the element and type the laterally umbrace length, and the information is can be displayed on this table information as well. And then once you set up all those features, and you can click the design on here. But to save our time, I just already clicked those design buttons. So let me move on to strength limit state flexure. So as you can see here, this one is check, which tells okay or not good. So as you can see here, most of the elements are fine, but you can see here element number 36 have a not good, and but here is a limited information we can review. So the thing you can if you want to see more detailed information, you can extract this information to extract the Excel report. So let me show you how to set up the Excel report. So click the position for design output on here, and you can select the position I and J, and as we see on here, the element number 36 has some problems. So let me just type the 36 on here on this box, and hit apply. And as you can see here, once you click the dot button, you can see the table information for the selected element. So here element 36 is selected. And then, oh my god. Sorry, I just forgot to turn on my screen. Oh my god. Sorry for my mistake on here. Let me let me go over those parts very fast. So the key points are very simple. So you define those features I already explained, and once you click the design button on here, and you can see the design result tables. So I open up the strength limit state flexure on here, and as I reviewed those tables, you can see on here on check columns, element 36 has like NG, which is not good. So if I want to see more detailed information through the Excel report, before you extract your Excel report, you need to define the element 36. So how you can do that? Go to position for design output on here, and select the element 36, and click apply on here. And once you click the dot box on here, as you can see here, you can see the table information. And then you can click the Excel report button on here. You can see the Excel report. But to shorten our time, I already made my Excel report on here. And there was some problems with element 36, as you can see on here. So if you want to see the more specific information on here, this one is element 36 report. So all the informations are like a punched on here. Once you click the extract Excel report, and scroll down, and on here minimum negative flexure concrete reinforcement, which is failed on here. So that's why NG comes out. And also flexure resistance based on box flanging compression. This one also failed. So that's why the flexure strength limit has failed on element 36. So first, once you're setting up all those design features, and go to design table, and or design result table, you can check very easily just by looking at the check columns, NG or OK. And if you find some critical location or critical element you want to see more detailed information, you can go to position for design output, and select the position you want to see, and click the Excel report, and you can see that those informations are punched on here. So today I just covered how to model a steel top bridge with using steel composite rigid, and node and element approach. So to shorten your time, you can use a wizard to automatically create the construction stages, and before composite and after composite load. And then you from that point you can make the more specific, more complex bracing system, such as inverted K bracing system or lateral bracing on the top flange by using node and translating or creating a node and element. And then you can do the design check, setting up the design check parameter, and extract your Excel report. Or if you find some critical element or failed element on design check table, you can using the position for output, and extract your Excel report. So this is all I would like to address. So thanks for coming this intro training sessions. And if you guys have more questions, what time is it now? Yeah, so we have a more case. We have like around 10 minutes. So if you guys have questions, could you guys send me questions under question tab? Give me a second. All right. Thanks for submitting your questions. I just see some of questions, and let me just demonstrate your queries. So, what is the difference between frame modeling and the other types of the modeling that you can select from at the beginning of the bridge widget? What is the difference between them? So this one is for the Can you guys see my screen on here? Okay. So on here, so modeling type, as you can see on here, R frame and R plate. But like there is a 4 different options. But the on the composite steel box or steel top sections, modeling type will be only available for R frame. This R frame, which means all the bridge information consists of beam element, not plate element or solid element. But if you select the deck as plate, girder as frame, that part can be modeled through the plate element, and the girder part will be created by a beam element. So maybe if you create your deck as plate, you're gonna get a more accurate result values. But the I guess R frame is very R frame can be is enough for doing the design check and some structure analysis, especially for design check. R frame is good to be used. Okay, give me a second. Okay, here is a technical issue. Give me a second.